Did you know that some planets may hide cores hotter than stars' surfaces? As you settle into the soft hum of the engines, that thought lingers in the back of your mind. The ship cradles you in its gentle vibration, console lights washing the cabin in shifting colors while the recycled air brushes against your skin. You've had a long day, maybe too long, and now all you have to do is breathe, sink into the quiet, and let the vastness outside the viewport draw you in. This journey isn't about rushing, it's about drifting, slowing, letting your thoughts fade as we guide you toward a world wrapped in shadow, mystery, and impossible depth. We start at its outer edge, a glowing veil of dust where light bends and dances in ways you've never seen. You hover there with me, just outside the atmosphere, watching the planet's surface shimmer under distant starlight. Take a moment, let the scales settle in. You're not landing, not yet. Instead, picture the ship easing forward, as if the planet itself is pulling you closer, welcoming you through its upper layers. No sound, no hurry, just a slow, graceful descent into the unknown. You might feel the ship shift slightly as we pass through clouds of strange vapor and threads of crystalline dust. A glowing shard drifts past your window, maybe a relic of something ancient, maybe just frozen light. It vanishes as quickly as it came. Below us lies a world, layered like a living story, a fragile outer shell, a deep and restless mantle, and at the very center, a core so extreme it borders on the impossible. And here you are, watching it all unfold, drifting deeper, one quiet breath at a time. We've never directly pierced these profound inner regions. No probe has filmed them. No human gaze has witnessed them firsthand. The deepest we've ever ventured into a world like this is merely to its upper crust, a shallow scratch in the grand scheme of things. Everything we know beyond that comes from the subtle echoes of gravimetric shifts, from energy waves rippling through its dense strata, and from the intricate shifting patterns of the magnetic field that shields this very world. And yet, from these faint, ethereal clues, a captivating picture emerges, one of immense heat, ceaseless motion, and continuous planetary transformation. Deep inside, this enigmatic world pulses with a vibrant inner life. Exotic elements flow, colossal currents churn, and heat radiates, slowly, imperceptibly, shaping the alien surface above. Vast mountain ranges rise, chasms open, and entire continental plates drift across its face, all orchestrated by the powerful forces hidden beneath. As we prepare our deeper descent, you might find yourself wondering what colossal energies stir in the perpetual dark. How does such a world maintain its internal inferno for billions of years? And why does this deep interior, a place we can never truly visit, hold such profound power over the outer shell we now perceive? These are the mysteries we'll gently explore tonight, softly, slowly, layer by shimmering layer. Our true journey begins here, on the outermost shell of this celestial sphere, the very boundary we now trace with our vessel. From our distant vantage point, it appears unyielding, an eternal shield against the void. But this exoplanetary crust, you see, is often far more delicate than it seems. Imagine it as the gossamer film on a cosmic bubble, a mere whisper separating us from the immense, churning interior. And this delicate skin isn't uniform. Oh no. We observe varying formations, towering continental analogues of lighter, crystalline compounds, often sculpted by ancient winds or stellar radiation. Then there are the vast sunken plains, akin to oceanic basins, composed of denser, dark, volcanic-like minerals. This subtle difference in mass is why some regions rise like monumental landmasses, while others recede into sprawling depressions, bathed in the distant starlight. Quite elegant, isn't it? This outer shell isn't a static blanket. It's a dynamic tapestry. Picture it gliding, almost imperceptibly, upon the viscous, semi-fluid layer beneath a subcrustal ocean of slow-moving matter. These immense segments aren't anchored, you understand. They journey, they converge, they fracture, then mend themselves anew. It's the very pulse of this world's outer geography. Vast tectonic plates, immense cosmic jigsaw pieces, perpetually adrift on a sea of molten rock and all. Their crawl is agonizingly slow from our fleeting perspective, maybe just centimeters a cycle. But across stellar millennia, their relentless ballet redraws the planet's entire visage. Isn't that just like space, always working on a time scale beyond our comprehension? Observe closely now. When two of these titanic slabs recede from each other, a fissure opens. From the depths, raw, molten energies surge upwards, crystallizing into pristine new surface. Material along colossal rift valleys, much like the spreading zones we've mapped on various young worlds, slowly expanding their cosmic frontiers. It's a quiet creation, unfolding even as we watch. But when they converge, that's when the universe truly flexes its power. One plate might bow, plunging into the fiery maw beneath, in a process we term cosmic subduction. As it descends, it vaporizes, fueling colossal eruptions that carve out chains of towering, active volcanoes, fiery coronas tracing the planet's active seams. Magnificent, isn't it? Nothing to worry about, probably. Then there are the regions where these plates merely brush past one another, a grating, sideways waltz along monumental fault lines. Here, the sheer friction. You feel that subtle vibration through the hull. That's just the ship adjusting. Or perhaps it's this world itself, gently sighing as its vast surface shudders. You feel it, don't you? This subtle shudder that courses through the hull, a faint, almost imperceptible tremor from the vast planetary body we now orbit. It's not a smooth, continuous flow, this movement beneath the surface, but a series of building tensions, a cosmic squeeze and release. When that pressure finally breaks, the very ground below us, hundreds of miles down, on that distant, veiled world, gives a planetary sigh, a deep rumble that resonates even up here. From this altitude, bathed in the gentle console lights of our bridge, its icy crust might appear utterly serene, yet it's anything but still. It's a vast, frozen shell in constant, grinding motion, fractured and reshaped by the slow, immense churn of forces hidden in its molten core. Colossal peaks, perhaps mountains of exotic frozen gases, slowly rise where immense tectonic plates collide, pushing skyward like slow-motion cosmic giants. Imagine cryovolcanoes erupting along deep rifts, spewing glittering dust and supercooled volatiles into the thin, alien atmosphere. Nothing to worry about, probably. These cosmic tremors mark the fracture lines where internal stress finally breaks free. This ceaselessly restless surface has sculpted not only the desolate landscape you see reflected in the forward viewport, but perhaps the very history of any life that might stir within its depths. The drifting of its colossal landmasses would surely reshape atmospheric currents and temperature zones, opening and closing migration routes for any indigenous fauna, bringing species into contact or sealing them off in profound isolation. Over eons, this churning crust writes the story of evolution in glistening crystalline formations, in frozen plains, and in subterranean ice caverns. Yet, this outermost shell is merely the prelude. Beneath it, a deeper engine hums, a core of exotic matter that drives this grand, slow ballet. The surface is just a thin veil. The heart of this world's motion lies much, much deeper. If you were to hold a fragment of this distant world in your hand, a shard of its crystalline peaks or a piece of its dark, abyssal floor, you would be grasping a tangible record of its birth, its unique chemistry, and its ceaseless internal dance. We carry a few such samples in the lab, illuminated by the gentle glow of the specimen bay. Its surface is composed of diverse compounds, arranged in intricate, often luminescent, crystal patterns formed under unimaginable pressures, intense thermal gradients, and the deep time of the cosmos. The most abundant elements, let's call them xylar and viridian for now, often form xylotic compounds, the very backbone of these alien formations. Picture light-hued, lower-density minerals that allow entire crystalline islands to ride higher atop the denser mantle, almost floating. Isn't that just like space? In stark contrast, the abyssal plains are often rich in heavier metallic alloys, contributing to their profound, inky darkness, where vast, ancient biomineral structures have slowly accumulated from the remnants of alien life or sedimentary debris. You find different textures, different hues, and scattered throughout are pockets of truly rare elements, glistening gems, or exotic ores that have been concentrated by geological processes over stellar ages. These are the shimmering veins of cosmic copper, the subtle seams of a strange golden dust, the deep pockets of hyperconductive elements that power our very ship, reflected in the subtle hum of the engines and the rhythmic ebb of recycled air. But while these surface treasures are sometimes within reach, much of this world's profound story lies hidden far beyond our touch. To truly fathom what stirs deeper beneath that ancient crust, we must get creative. Our most advanced subsurface probes, autonomous drilling bots with their energy drills, offer the most direct path downward. Yet, even our most ambitious attempts have barely scratched the surface. The deepest we've ever managed, on a different icy moon, only pierced a few dozen miles, a mere scratch. Temperatures and pressures, combined with the exotic material composition, became so intense that deeper progress proved impossible. And yet, that narrow tunnel offered a glimpse into primordial strata, older than anything known in our home system. To delve deeper still, we rely on indirect methods, most notably the study of planetary tremors. When a deep internal moonquake or planet shudder occurs, it sends out ripples of cosmic resonance through the world. These waves travel at different speeds depending on the density and composition of the exotic fluids or solid metallic cores they pass through. Some waves can pass through liquid, others cannot. Some bend and refract in peculiar ways, others simply bounce. By deploying sensitive orbital resonance trackers and surface-hugging sensor arrays across the globe, we can meticulously track how these waves move. This data allows us to infer the subterranean structure and composition of the crust and the enigmatic layers below. Seismic tomography, much like a holographic CT scan of an entire world, allows our ship's computers to build intricate three-dimensional maps of crustal thickness, deep-seated faults, and active subduction zones. These images, shifting and morphing on the main display, reveal the hidden boundaries of tectonic plates, the presence of buried crystalline mountain roots, and the slow, creeping movements of deep strata miles below the surface. With enough data, Sometimes we can even discern rising plumes of superheated mantle rock slowly ascending that may someday pierce the surface to form new cryovolcanic peaks. You might need a moment to just float here, watching these ghost images of a world's heart. Other tools assist our quiet observations as well, their data points flickering across our console lights. Gravitic sensors measure subtle variations in the world's gravitational pull, revealing hidden densities of lighter or heavier subterranean masses. Magnetospheric scanners track the delicate shifts in the planet's magnetic field, hints of buried veins of exotic mineral deposits, and hyperspectral orbital imaging reveals surface deformations and slow uplifts that whisper of immense forces building from below. Together, these disparate methods converge, forming a layered understanding of a world we can never truly touch. We map its churning outer shell, not with our hands, but with echoes, with field distortions, and with streams of data, slowly piecing together a picture of this cosmic body's restless skin. It's quite the cosmic puzzle, isn't it? And yet, this outer shell isn't merely a boundary. It is, perhaps, a conduit, a gateway. Everything above us, every exotic flora, every towering alien spire, every atmospheric tide is fundamentally sculpted by what happens deep below. This alien crust is where a world's deep physics intertwines with its burgeoning life. While it may seem like just a thin outer shell for any life on this distant sphere, this fragile crust is everything. It is the stage upon which alien ecosystems unfold, the anchorage for colossal root structures, the very source of every element those alien metabolisms require, and the protective boundary that shelters them from the volatile, raw energies of the deep. Without this crust, there would be no stable land masses, no regulated atmospheric cycles, no substratum for alien jungles, and no refuge from the stellar winds or the intense, simmering heat of its core. Why does the universe always do its to you? In its uppermost layers, the crust slowly erodes over eons, broken down by alien winds, corrosive precipitation, or vast glacial creeps. This weathering releases vital trace elements, which flow into subterranean currents, accumulate in nutrient-rich dust clouds, or seep into hydrocarbon seas. Elements crucial to alien metabolisms, perhaps alien calcium, potassium, iron, or phosphorus equivalents, all originate from this slow cosmic erosion of ancient rocks. Even the complex atmospheric regulation of the planet, which governs its climate over geological time, is tightly bound to this surface. Atmospheric gases, reacting with surface compounds, dissolving into a weak alien acid, slowly sculpt the landscape and regulate the world's thermal balance, a delicate dance of cosmic chemistry. As those minerals gently settle, they carry carbon deep into the ocean's silent embrace, eventually becoming part of ancient limestone and other sediments. Over eons, a slow, patient dance begins beneath you. The immense forces of plate tectonics lift these layered memories, forming new mountains that reach for the stars, returning that stored carbon to the atmosphere through gentle volcanic whispers. It's an unbelievably long, steady rhythm, but one that keeps the planet's delicate balance just right for life to unfurl. Without this endless renewal and careful recycling of its outer skin, the world's atmosphere and oceans might become truly inhospitable, unbalanced. A soft tremor from the ship's quiet engines accompanies this thought. You might need a moment to just float here, letting the sheer timescale of it all settle. Quite the delicate dance, isn't it? This crust, this surface we've been observing, also meticulously sculpts the very landforms that define entire ecosystems and climates. Think of vast mountain ranges, quietly dictating rainfall patterns and temperatures, or the deep ocean basins, choreographing the grand circulation of currents. Ridges, valleys, and even the fiery birth of volcanic islands all carve out unique niches where life, in its incredible diversity, can flourish, thriving in every crack, every edge, every margin of this dynamic, shifting shell. But even as we marvel at its surface beauty, we must peer deeper to truly grasp the hidden mechanics of its restless nature. A faint hum resonates through the deck plating as we adjust our approach. Starlight reflects off the polished control surfaces, hinting at the vastness beyond. For you see, this crust doesn't just move on its own accord. Its profound restlessness is powered from far below by the immense heat steadily rising from the mantle, and by even deeper, more fundamental forces within the very heart of the planet. And one of the most profound, yet invisible, connections between this outer shell and the Earth's fiery interior isn't found in rock or temperature, but in something unseen: its magnificent magnetic field. This vital shield is meticulously generated within the outer core, where molten iron and nickel swirl in complex, powerful currents, creating a colossal This invisible generator then produces a protective bubble, the magnetosphere, which gracefully envelops the entire planet, shielding it from the harsh kiss of the solar wind. Without this incredible, invisible barrier, the high-energy particles constantly streaming from the sun would gradually, inexorably strip away our atmosphere, much as they did on Mars, leaving behind a desolate, airless world. Early life, especially, would likely never have had the chance to take root and flourish without this silent guardian. And yet, the crust itself plays a critical role in how we even begin to comprehend this field. As molten lava cools and solidifies at the surface, tiny iron-bearing minerals within it naturally align themselves with the prevailing direction of Earth's magnetic field. These microscopic compass needles then become locked firmly in place, faithfully recording the field's strength and orientation at the precise moment the rock formed. Isn't that just like space, full of such elegant, unexpected archives? Over immense spans of time, as tectonic plates patiently carry these rocks away from their spreading centers, we can meticulously read the magnetic patterns they leave behind. Think of them as lines in an ancient, cosmic book, telling the grand history of Earth's magnetic reversals, those moments when north became south and south became north. Some crustal rocks are magnetized so intensely that they create local magnetic anomalous subtle deviations in the field that reveal both the ancient behavior of the magnetic shield and the stately movement of plates over hundreds of millions of years. So, in this extraordinary way, the crust is far more than just the planet's outer shell. It is a living archive, a geological library of unimaginable scale. It holds the silent story of deep time, of shifting continents, of ancient climates, and of a planet constantly shaped by what lies far beneath its visible surface. The crust not only supports life but preserves its history, bearing the indelible imprint of that fiery, hidden heart deep below. And now, as we gently leave the familiar crust behind, our subtle ship shifts again. The distant starfield seems to blur slightly as our velocity increases for the descent. We begin our quiet journey now into that deeper world, to the vast, flowing mantle, where stone behaves like a slow-motion liquid, and the very engine of the Earth begins its stately, powerful turn. You might feel a gentle, almost imperceptible shudder through the deck as our inertial dampeners compensate for a minor shift in our course. If you've ever stood atop a soaring mountain ridge, or felt the distant tremble of an earthquake beneath your feet, or perhaps seen the ethereal steam rise from a hot spring, you've witnessed the outer echoes of Earth's profound inner workings. The crust, while appearing a stable stage, is in constant, dynamic dialogue with the planet's deeper layers. Mountain ranges, for instance, form where crust is forced upward, the majestic result of colossal plates grinding slowly, relentlessly together. Beneath the towering Himalayas, the Indian plate presses into the Eurasian plate with an unrelenting force, creating not only those soaring, cloud-piercing peaks, but also incredibly deep roots that extend far down into the mantilla mirror image of the surface, buried in utter darkness. Volcanoes also offer a direct, fiery connection to the mantle below. At rift zones and subduction boundaries, molten magma rises through cracks in the crust, bringing with it the unique chemistry and immense heat of the deep earth. Each eruption paints the surface with material from miles below, forming new islands, dramatically altering landscapes, and sometimes even shaping entire global climates. Even the gentle steaming of a geothermal spring whispers secrets of that hidden world of mantle heat, warming water deep beneath our feet, rising through delicate fractures in stone. Nothing to worry about. Probably, the ambient lighting in the cabin might dim ever so slightly, inviting a deeper sense of introspection. These surface phenomena are not isolated events. They are profound messages, quiet signs of slow, incredibly powerful processes unfolding far beneath our visible world. Earthquakes record the sudden release of immense stress built up over decades, sometimes centuries. Uplifted plateaus and dramatically folded rocks speak eloquently of the crust buckling under colossal, deep-seated pressure. Every hill, every basin, every rift, and every vibrant reef has been shaped not merely by the erosion of weather and the passage of time, but by the stately, inexorable movement of stone deep inside the earth. The crust, then, is only the surface of the story. To truly understand the full, sweeping tale, we must go deeper. And so now we quietly leave this outer shell behind. The engine's soft hum, a constant, reassuring presence, and begin our true descent into the mantle. Beneath the crust lies this mantle, a vast, powerful, almost unimaginable realm of rock, so deep and dense that it holds the overwhelming majority of the planet's entire volume. It stretches from just below the crust beginning, around 20 kilometers down beneath continent sand, continues for more than 1,800 kilometers beneath our feet, nearly halfway to the Earth's very center. The recycled air feels perfectly tempered, and a stray thought drifts through your mind. So much complexity hidden beneath the surface. But this mantle is not uniform. It's a layered enigma. It's conceptually divided into two major zones, the upper mantle and the lower mantle. These aren't separated by a sharp, distinct line, but rather by gradual, profound changes in pressure, in temperature, and in the very behavior of the rock itself. The upper mantle, closest to the crust, is the most dynamic, the primary driver. This is where slow, creeping convection currents tirelessly rise and fall, transporting immense heat from the deep earth upward and, in doing so, gently moving the colossal tectonic plates at the surface. While the rock here is technically solid, it behaves with the viscosity of an incredibly slow-flowing fluid. Over vast spans of time, it bends and deforms, creating the very movement that drives earthquakes, sculpts mountains, and fuels volcanic activity. A soft, almost imperceptible vibration travels through your seat, a testament to the ship's quiet power. And so, as we simply drift here, the gentle thrum of the ship's engines, a soft whisper against the recycled air. Let's turn our gaze to something much closer, yet equally mysterious. The very heart of that vibrant blue sphere suspended outside our viewport. You know, it's not just the surface that tells Earth's story. Far beneath the oceans and continents, where the pressure becomes unimaginable, the materials themselves shift and change, a deep, silent ballet playing out over eons. These subtle transformations in the rocks make up slow its journey and even alter how energy ripples through it, a cosmic sonar, if you will, allowing clever minds back home to map these profound boundaries from afar without ever having to touch them. Pretty neat, isn't it? Deeper still, past that initial frontier, you find yourself in the lower mantle, a realm where gravity asserts its dominance with crushing force. Here, the rock doesn't just exist. It's alive with heat, denser and more unyielding, a molten sculpture held in place by sheer cosmic weight. It flows, yes, but with an almost glacial slowness, like thick, ancient honey, carrying warmth from the fiery core up toward the calmer surface. This incredible slow-motion circulation of solid rock, what they call mantle convection, is the planet's silent heartbeat, the engine that keeps Earth breathing, geologically speaking. Without it, well, the crust would just seize up. The continents would freeze in place, and that dynamic blue marble would become a static, lifeless thing. A chilling thought, really. Isn't it wild to consider that what we perceive as solid ground, something so firm beneath our feet, is actually a vast, slowly churning ocean? Over countless millennia, this seemingly solid rock flows inch by agonizing inch, a profound, creeping motion driven by an immense internal warmth. It's the grand architect behind the wanderings of continents, the quiet birth of new ocean floors, and the majestic rise of those towering mountain ranges you can just make out from here. From our quiet perch amongst the stars, the Earth's surface might seem to shift by mere finger's widths each year. But remember, those gentle twitches are the result of gargantuan forces welling up from the planet's very core. Imagine it like a colossal pot of exceptionally thick, heavy soup, boiling with an almost imperceptible slowness, deliberate and utterly constant. Close to the planet's incandescent heart, the rock absorbs incredible heat, growing ever so slightly lighter, more buoyant, and like a gentle balloon, this warmed material begins its long, languid ascent towards the surface. As it nears the cool embrace of the crust, it slowly sheds its warmth, spreading out like a subterranean current before eventually, inevitably, sinking back down into the depths in cooler zones. These enormous, patient cycles of rising and sinking rock aren't just fascinating. They form an invisible, endlessly looping conveyor belt beneath the colossal tectonic plates you've heard about. It's truly mesmerizing to think of those vast continental rafts simply riding atop these slow-motion currents, carried along by the very flow of the mantle beneath them. Where this deep mantle material gently pushes upwards, you often find those incredible mid-ocean ridges, the colossal underwater mountain ranges you occasionally see mapped, where new crust is patiently forged as plates are nudged apart. And conversely, where it quietly descends, we discover subduction zones, those geological abysses where one enormous plate is slowly relentlessly dragged back into the deep earth like a cosmic recycling system. Even those seemingly serene, quiet expanses of interior land, far from any visible plate boundary. Feel the subtle influence of this deep, slow-motion ballet, either gently rising or stretching over unimaginable spans of millions of years. But what, you might wonder, fuels this endless, patient dance? Where does the mantle get the immense heat it needs to keep moving, ever so slowly? Well, a portion of that inner warmth, the initial spark that set everything in motion, is primordial. It's the ancient echo of Earth's violent birth over 4.5 billion years ago. A whisper from a time when particles collided and merged with cataclysmic energy in the young solar system. That raw, incandescent heat has been patiently leaking away ever since, a slow bleed through the planet's crust and out into the cold embrace of space. You can almost feel the residual warmth, can't you, even from out here? But if that initial surge of birth heat were the only source, our beautiful blue world would have chilled to its core and gone silent ages ago. No, there's another, quieter force at play, a hidden furnace keeping the interior warm even today. This quieter, yet utterly crucial, process is known as radioactive decay. It's a remarkable phenomenon where certain elements nestled within Earth's rocky depths, like uranium, thorium, and potassium, are naturally unstable. Over unimaginable stretches of time, their individual atoms meticulously break down, settling into more stable forms, and in doing so, they gently, patiently release heat. It happens at an incredibly steady, predictable pace, and the energy it produces, cumulatively, is immense. Each atom might contribute only the faintest warmth, a cosmic sigh. But consider how many radioactive isotopes are scattered through the Earth. Together, they contribute a truly significant, silent portion of the mantle's deep, patient warmth, like a long-burning fire, quiet but unceasing. Most of these heat-generating elements are concentrated within the crust and the upper mantle, where they continue their quiet work, steadily warming the surrounding rock. That deep warmth then rises, becoming the primary driver for the convection currents in the deeper layers, turning the planet's interior into a slowly simmering pot. In this way, radioactive decay acts as a patient, enduring hearth deep within the Earth, a steady, unfaltering source of energy that has powered the planet's dynamic interior for billions of years. It's this incredible combination, the residual heat from creation and the ongoing, quiet power of radioactive decay, that ensures the mantle remains ceaselessly active. Without it, the rock would eventually grow still. The slow, majestic convection would halt. The plates above would simply cease their ancient dance. Imagine a world without that inner fire. There would be no towering new mountains pushing skyward, no fresh volcanic islands gently rising from the ocean's embrace, no constant renewal of the crust. The very face of our Earth would slowly, irrevocably change, not in a sudden cataclysm, but as the quiet, internal warmth gradually faded. But as long as these powerful heat sources persist, the mantle will continue its slow, powerful, and utterly invisible work, patiently shaping the world above, an unseen sculptor moving mountains and oceans with the grace of geologic time. You might need a moment to just float here, letting that sink in. It's a profound thought, isn't it? Yet, not all that incredible heat within the mantle rises in those neat, smooth, symmetrical convection cells we've been imagining. Sometimes, the universe has a way of surprising us with its localized intensity. In certain rare places, narrow, exceptionally hot columns of material, almost like incandescent fingers, surge directly upward from deep within the mantle, possibly even originating at that profound boundary between the mantle and the core itself. These are what geologists call mantle plumes, and where they finally reach the robust base of the crust, they can ignite persistent volcanic activity that can last for millions of years. Imagine a cosmic welding torch patiently burning through layers of rock. One of the most beautifully clear examples of such a mantle plume lies beneath the vast, serene expanse of the Pacific Ocean, responsible for that breathtaking chain of volcanic islands we call Hawaii. Unlike most volcanoes, which tend to huddle along the restless edges of tectonic plates, the Hawaiian Islands emerge majestically in the very middle of the enormous Pacific Plate. They weren't born from the crashing embrace of colliding plates or the slow descent of subduction zones, but rather from a remarkably stationary plume of intensely hot mantle rock steadily rising beneath a plate that is anything but stationary. Isn't that just like space? A beautiful contradiction. As the colossal Pacific Plate gently, imperceptibly drifts northwestward across this unmoving mantle plume, the plume acts like a powerful, persistent punch, breaching the crust again and again, patiently forging one volcanic island after another. The verdant Big Island of Hawaii, the youngest, currently sits directly above this fiery hotspot, still actively growing. Older islands, like the tranquil Maui and bustling Oahu, were once in that very same spot but have since quietly drifted away, becoming volcanically serene. Even further to the northwest, almost lost in the deep blue, are ancient seamounts. Once majestic volcanoes, now submerged beneath the waves, tracing a silent breadcrumb trail of the plate's slow journey over the stationary plume. This incredible geological breadcrumb trail isn't just a beautiful sight. It offers us powerful, undeniable evidence of both the constant, imperceptible motion of the tectonic plates and the complex dynamic behavior of the mantle itself. It whispers to us from the depths that the mantle isn't a uniformly churning mass, but contains these focused, enduring upwellings of fiery material capable of sustaining volcanic life for tens of millions of years. Some scientists, peering into these ancient mysteries, even believe these plumes might begin their epic ascent near the core mantle boundary, patiently rising more than 1,800 miles through solid rock before finally reaching the surface. Truly a testament to Earth's immense, unseen power. But how, you might calmly ask, do we know what's happening in such unimaginable depths, in a place we can never physically reach, even with all our advanced sensors and instruments? The answer lies in one of Earth's scientists' most elegantly sensitive tools, seismic waves. When the planet shudders with an earthquake, it broadcasts vibrations outward in all directions. Much like the perfect ripples you might see spreading across a still pond. But these ripples travel not through water, but through the immense, solid rock of the earth, each one a messenger from the deep. And here's the clever part. These waves travel at different speeds, whispering secrets about the temperature, density, and composition of the material they pass through. They are our eyes and ears, patiently listening to the planet's silent heart. The distant hum of the ship's engines is a comforting vibration, a soft whisper against the hull that becomes part of the silence around us, much like how subtle tremors ripple through a world. You might not notice it at first, this gentle thrum, but it's always there, a constant companion in the cosmic void. And just as our ship sends out signals to navigate the stars, planets send out their own, telling tales of what lies beneath their stony surfaces. We're learning to listen to these deep planetary echoes, to understand their hidden language. Nothing to worry about, just the universe sharing its secrets, wouldn't you say? Imagine these echoes as two distinct voices, two types of seismic waves. The first, you see, are like whispers that glide through anything: solid rock, liquid oceans, even the gaseous atmosphere, incredibly fast, a true rush of information. We call them P waves or primary waves. But then there are the S waves, secondary, more particular. They're a gentle sway, a slow, elegant ripple that absolutely refuses to pass through liquids or gases. They prefer the sturdy embrace of solid rock, which, for us, is incredibly useful. It's like having a special sensor that can tell you exactly where the molten, fluid heart of a world truly begins. So, as we drift here, watching the starlight play across the muted glow of the console, consider how these internal vibrations paint a picture. When a planet trembles, these waves move through its layers. If an S wave suddenly vanishes, it's telling us something important. Here, my friend, is a sea of molten rock or liquid metal, and in certain warm, rising currents deep inside, these waves even slow down, as if easing into a cozy, heated pool. We call these low-velocity zones, areas where the material is warmer, more yielding, perhaps even partially melted. It's like finding a warm pocket in the vastness, isn't it? By meticulously mapping these zones beneath what we call hotspots on a planet's surface, we can trace the hidden pathways of these internal currents. It's a bit like using the ship's advanced scanners to visualize an unseen nebula, isn't it? Through a technique we beautifully name seismic tomography, we gather whispers from thousands of planetary sensors, stitching them together into a stunning, three-dimensional image of the deep interior. It's like seeing the world's heart in soft, swirling shades of hot and cold, revealing features like the immense Hawaiian plume or the sprawling African superplume. Truly, these distant vibrations reveal what would otherwise remain utterly invisible to us. They show us narrow rivers of incandescent rock flowing upward through a world of stone, connecting the deepest layers to the surface. Seismic waves are, in essence, the echoes narrating their incredible journey. Now, the idea of rock flowing might sound a little contradictory, I know. After all, we usually think of stone as unyielding, rigid, something utterly unchanging. But deep within the mantle, under unimaginable pressure and searing heat, solid rock behaves in ways that utterly defy our everyday experience. It doesn't melt into a liquid, not exactly. Instead, it moves, stretches, bends, and deforms with a kind of slow, ponderous grace that only becomes apparent across truly vast spans of time. This fascinating phenomenon is what we call viscous flow. It's not because the material is liquid, but because the intense heat and pressure make it behave more like a thick, sluggish syrup than a brittle, fracturing solid. The rock doesn't crack or shatter down there. Instead, it slowly, patiently changes shape as it flows in immense convection currents beneath the surface. Can you imagine? Even at temperatures soaring past 1,000 degrees Celsius and pressures that would utterly crush our sturdy hull, the mantle remains solid, yet it moves. It's a remarkable in-between state, vital to the planet's long-term evolution. While its flow isn't visible to the eye, it's entirely measurable, slowly carrying heat from the deep interior up toward the crust and transporting cooler material from the surface back down. These slow circulating currents are the hidden engine for so much of what we see on a world's surface. From the majestic drift of continents to the fiery birth of volcanoes, the consequences of this silent internal ballet ripple outward, affecting the crust, the vast oceans, and even the very atmosphere. Isn't that just like the universe, making the invisible so profoundly impactful? The influence of the mantle on a planet's surface geology is simply immense. Wherever this hot mantle material rises, it gently pushes upward on the crust, creating subtle bulges that can lead to the formation of towering plateaus, deep rift valleys, or sprawling volcanic fields. Consider the East African Rift, for instance. It's a place where the crust is slowly, incrementally being pulled apart by an upwelling of mantle material, carving out immense valleys and scattering volcanoes across the landscape. This process, unfolding over millions upon millions of years, is quite literally tearing a continent in two. Volcanic activity, fiery and spectacular, is one of the most visible outcomes of this deep mantle behavior. Where hot plumes ascend from far below, they melt portions of the upper mantle, generating bubbling magma. This molten rock, buoyant and incredibly hot, patiently makes its way through any weaknesses in the crust until it finally erupts at the surface. Over vast stretches of time, repeated eruptions build up those majestic volcanoes you see, towering landforms that can stretch miles into the sky, influencing regional climate, nurturing unique ecosystems, and even shaping the evolution of life itself. Different types of mantle material, you see, produce different styles of volcanism. Hot, less viscous magma tends to create those broad, gentle shield volcanoes, like the ones you've perhaps seen data on from Hawaii's slow, steady flows. Cooler, more silica-rich magma, however, leads to far more explosive eruptions, violent outbursts like those documented in the Pacific Northwest or even the ancient Mount Vesuvius. These aren't random occurrences. They reflect deep-seated variations in mantle chemistry and temperature that have slowly built up over geological eons. A quiet thought: the world is truly a master of subtle, profound artistry. The mantle also quietly influences the long-term stability of the crust itself. In regions where the mantle is unusually hot or buoyant, the crust can become thinner, more stretched, creating expansive rift zones and basins. Conversely, cooler, denser parts of the mantle can gently pull down on the crust, contributing to the slow, relentless sinking of oceanic plates into vast subduction zones. Even entire continents are influenced by the mantle's slow, rhythmic rise and fall. As these deep currents shift, they can lift vast land masses or allow them to slowly sink. This majestic vertical motion, which we call dynamic topography, subtly changes sea levels over geological timescales, alters drainage patterns, and sculpts the evolution of coastlines over tens of millions of years. So, while the mantle lies utterly hidden beneath hundreds of miles of solid rock, its influence is absolutely everywhere in the very shape of the land. The precise placement of volcanoes, the intricate patterns of earthquakes, and the slow, stately rearrangement of continents across the face of the planet. It is, in essence, the deep, warm heart of a world's surface story, the ultimate silent architect. As our gentle ship carries us onward, letting the faint scent of recycled air fill the quiet cabin, let's imagine we're descending even deeper, leaving the mantle behind to enter a realm of staggering extremes. We're moving towards a world of crushing pressure, unimaginable heat, and metals that behave in ways no surface material ever could. This is the Earth's core, the fiery, metallic heart of the planet, hidden more than 3,000 kilometers beneath your feet, though no human instrument has ever physically reached it. We are remarkably confident about what lies below because of the way those seismic waves move through the planet during quakes. These vibrations act like sonar, revealing not only the precise shape and depth of the core, but also its truly unique internal structure. And what they reveal, my friend, is extraordinary. The core is made primarily of iron, heavy and dense, with smaller amounts of nickel and traces of lighter elements like sulfur, oxygen, or silicon. It's a world within a world, a secret known only by the echoes. And as we journey further into the heart of things, we discover that beneath those familiar landscapes, nestled deep within our home world, lie elements of extraordinary density. Imagine them, gravitationally pulled inward by immense forces, forming the very anchors of the planet. It's astounding to consider, but this innermost core, though only a fraction of Earth's total volume, actually holds about a third of its entire mass. Picture our young Earth, a swirling, fiery crucible, entirely molten in its infancy. Over cosmic stretches of time, the heaviest elements, like iron and nickel, began their slow, deliberate descent, sinking towards the absolute center. Meanwhile, the lighter materials gracefully ascended, forming the outer layers we know today. This beautiful dance of planetary differentiation, a cosmic sorting, is precisely how our world sculpted itself, with its distinct core, mantle, and crust. A steady, gentle hum resonates through the hull of our vessel, a comforting thrum that mirrors the deep, patient processes we're observing. This ancient heart has remained a timeless echo of Earth's genesis, gradually cooling and evolving beneath countless miles of solid rock. Yet, it's not a uniform entity, not a singular, simple sphere. No, it's composed of two wonderfully distinct layers, separated not by what they're made of, but by their very state of being. You see the faint glow of the console lights reflecting off the viewport, painting the distant starlight in hues of soft blue and green, and you realize how clearly defined this separation is. The outer core, a vast ocean of liquid metal stretching for thousands of kilometers, continuously churns and swirls, driven by the intense heat radiating from even deeper within. Then, cradled inside this molten sea, lies the inner core, a solid sphere, about the size of our moon, where pressure is so immense it compels iron to remain solid, even as temperatures soar to a blistering 10 degrees Fahrenheit. A quiet marvel, wouldn't you agree? This delicate balance, liquid outside, solid within's one of Earth's most remarkable features, an eloquent testament to the power of pressure and heat. The outer core behaves with the grace of a fluid, its currents and eddies swirling in a cosmic ballet, playing an absolutely crucial role in generating the very magnetic field that protects us all. Conversely, the inner core, rigid and dense, continues its slow crystallization, a quiet growth over eons, as the planet gradually releases its primordial heat. The boundary between these two states is remarkably sharp, almost like a meticulously drawn line. You can almost envision a boundary that geophysicists have precisely mapped by listening to the planet's internal whispers. Nothing to worry about, probably. When seismic waves, Earth's own sound waves, pass through this boundary, they tell a profound story. Certain types of waves, the S-waves, simply vanish when they encounter the liquid outer core, unable to traverse such a fluid medium. But their companions, the P-waves, continue their journey, bending and shifting speed as they encounter materials of differing densities. By meticulously studying these subtle shifts, scientists have charted the precise edges of Earth's deep heart, confirming its dual nature, its liquid cloak and solid core. Though sealed away beneath thousands of miles of rock, this core is not isolated from the world above. Oh no, it's intimately connected, playing an absolutely vital role in countless aspects of Earth's behavior, particularly in safeguarding life on the surface. We feel a soft, almost imperceptible vibration through the hull, a gentle reminder of the immense unseen power at work. As we imagine delving deeper past the crust and mantle, the conditions become progressively more extreme. At the very center of Earth, more than 6,000 kilometers beneath your feet, the environment is unlike anything else imaginable on our planet. Here, the temperature rivals the surface of the sun, soaring to an estimated 10 degrees Fahrenheit. And yet, the pressure is so extraordinarily immense, over 3.5 million times greater than the atmospheric pressure at sea level, that even familiar metals behave in profoundly unfamiliar ways. Isn't that just like space, always full of surprises? In this bewildering environment, iron crystallizes into a solid form despite the searing heat. Its atoms packed so tightly together that the inner core is thought to be primarily solid iron, with hints of nickel and perhaps other lighter elements. The surrounding outer core, though slightly cooler, remains ferociously hot and stubbornly liquid, a churning ocean of molten metal enveloping that solid, burning heart. The pressure is so intense, in fact, that if you could somehow hold a piece of the inner core in your hand at the surface, it would instantly vaporize into nothingness. The materials existing at this depth can only maintain their stability under such extreme confinement. It is precisely these unusual, delicate conditions, this breathtaking balance between unimaginable heat, crushing pressure, and constant flow, that make the core so indispensable to life above. You might need a moment to just float here, suspended, absorbing the sheer wonder of it all as the recycled air gently circulates around you. Because this outer core is liquid, and because it's in perpetual motion, it acts as a magnificent dynamo, a colossal, natural generator of electricity and magnetism. As molten iron and nickel tirelessly swirl around the solid inner core, their motion gives rise to a vast, invisible force field that extends far into space, a protective embrace we call the geodynamo. It's a beautifully simple principle. Moving electric charges generate magnetic fields. Within the core, this iron-rich fluid is an excellent electrical conductor. As it moves, driven by the planet's internal heat and its stately rotation, it sets up immense circular currents, which in turn generate magnetic fields. Through an intricate, elegant feedback process, these fields organize into a coherent, planet-wide shield surrounding Earth in a protective bubble known as the magnetosphere. This magnetic field isn't static, not by a long shot. Oh no, it breathes, it pulsates, it subtly drifts, and over vast geological timescales, it even reverses its polarity. Imagine that. Ancient geological records, beautifully preserved within rocks, reveal that Earth's magnetic poles have flipped countless times in the past, sometimes every few 100,000 years, sometimes after much longer stretches of stability. These reversals are entirely natural, and while their exact triggers are still a subject of quiet scientific fascination, they are believed to originate in the subtle fluctuations within the powerful currents of that liquid outer core. The ship drifts ever so gently, a barely perceptible shift in gravity, a silent acknowledgement of these profound, slow-motion planetary dances. What makes this magnetic field so absolutely vital isn't merely its existence, but its tireless role in shielding all life on the surface. Without it, the torrent of charged particles streaming from the sun, the solar wind, would strike Earth's atmosphere directly, gradually stripping it away into the void. Look at Mars, where its weak or absent magnetic field has left the planet desolate, dry, and airless. But here on Earth, our magnificent magnetosphere deflects most of these destructive particles, safeguarding both our atmosphere and the precious organisms that depend on it. These high-energy particles are gracefully funneled along the magnetic field lines towards the poles, where they interact with molecules in the upper atmosphere, creating those breathtaking, glowing curtains of light we call the auroras, the northern and southern lights. These shimmering, glowing waves are far more than just beautiful spectacles. They are vivid, visible reminders of the deep, hidden forces tirelessly churning thousands of miles beneath our feet. So, in a very real and profound way, the continuous, restless motion of molten metal in Earth's outer core is what fundamentally makes life on the surface possible. It is a silent, unseen process, a majestic connection between the very heart of the planet and the boundless sky above. This magnetic field, a constant companion to our world, is more than just a curious phenomenon. It is an indispensable protective shield, one that has guarded life through countless eons. For billions of years, a silent, invisible shield has embraced our home world, a guardian born deep within its heart. You might not feel it from up here, drifting quietly with the gentle hum of the engines, the soft glow of the console lights casting a warm sheen over your controls. But it's always there. This vast magnetic bubble deflects the relentless solar wind stream of charged particles constantly exhaled by the sun, pushing against the hull of our ship with an almost imperceptible pressure. It's a remarkable defense, diverting most of that cosmic barrage around our planet, much like water flowing around a smooth, ancient stone. Without it, the sun's harsh energy would slowly peel away Earth's delicate atmosphere, just as it has on those barren worlds, Mars and Mercury. Quite clever, isn't it? More profoundly, this magnetic embrace safeguards the very blueprint of life itself. Those high-energy particles from the sun could easily damage the intricate strands of DNA, leading to a cascade of mutations that delicate ecosystems simply couldn't endure. But thanks to this magnificent unseen force, most of that harmful radiation is either blocked entirely or gently guided toward the polar regions. And when these solar particles do eventually dance into the upper atmosphere, they interact with the molecules high above the surface, painting those breathtaking, shimmering curtains of green, blue, and violet we call the auroras. They're not just beautiful, they're visual evidence, a whisper of the colossal engine turning silently at Earth's very core. Isn't that just like space, hiding its most vital secrets right under our cosmic noses? Yet, for all its immense importance, that deep, churning core remains profoundly out of reach. No probe has ever journeyed into its fiery embrace. No drill has even pierced the outer layers of the mantle, let alone hinted at the metallic heart within. So, how do we know what's truly down there? Our understanding comes from a combination of ingenious, indirect methods, like listening intently to Earth's own vibrations. Imagine our ship gently swaying in the void, feeling the subtle shifts of distant gravity. Earth scientists have learned to do something similar, using seismology, the study of tremors within the planet, especially those born from earthquakes. When an earthquake rumbles, it sends out waves that travel deep through the planet's interior, carrying precious information. These waves move at different speeds, depending on the material they traverse, bending or reflecting when they encounter boundaries between layers, almost like light passing through different densities of liquid. By carefully analyzing how these seismic waves behave on their journey, we can reconstruct the planet's internal structure, its size, its density, even the state of its core. There are two main types: P waves, which can glide through both solids and liquids, and S waves, which are much pickier, only moving through solids. When S waves simply vanish, failing to appear on the opposite side of the planet after an earthquake, it immediately reveals the presence of a liquid layer, in this case, the swirling outer core. The P waves, meanwhile, slow and bend as they navigate this molten ocean, then pick up speed again as they plunge into the solid inner core. Such precise changes in their journey offer incredibly detailed measurements of the core's depth, its mysterious shape, and its composition. Quite clever, really, for beings who can't even visit the place. Beyond mere vibrations, we also listen to the subtle whispers of Earth's magnetic field. Geomagnetism offers another window into the core's dynamic behavior. You might feel a faint ripple as the ship's own magnetic sensors register distant stellar phenomena, a gentle reminder of the invisible forces at play. By meticulously tracking minute changes in Earth's field over time, scientists can model the immense, swirling currents of molten metal within the outer core. Fluctuations in magnetic strength and direction reveal how those deep currents are shifting, how the planet's grand geodynamo is evolving, perpetually generating the protective shield we observed earlier. Satellite missions, like ESA's swarm constellation, act as vigilant sentinels, continuously monitoring this magnetic field, capturing its small variations with extraordinary precision. Combined with high-pressure laboratory experiments and complex computer simulations, these techniques weave a surprisingly detailed understanding of a place we cannot touch, a secret world of metal, heat, and ceaseless motion, sealed away at the very center of our Earth. You have to wonder, don't you? What other secrets does it hold? For all that we've pieced together about Earth's fiery heart, it remains one of our planet's most enigmatic regions of place. We know only through those faint vibrations and magnetic whispers. Many of its behaviors are still far from fully understood, and it seems each new discovery only unveils another layer of fascinating uncertainty. One such puzzle is the curious rotation of the inner core itself. Seismic data hints that this solid inner sphere might spin slightly faster, or perhaps even slower, than the rest of the planetary phenomenon known as differential rotation. Some studies suggest it speeds up and slows down in cycles that might even be intrinsically linked to changes in Earth's overall magnetic field. But the exact cause, its precise rate, and the ripple effects of this strange motion remain hotly debated. Always more layers, aren't there? Just when you think you understand. Even the age and very formation of the inner core are subjects of ongoing scientific inquiry. While Earth itself is an ancient, venerable world, over 4.5 billion years old, its solid inner core might be a relative newcomer, perhaps having formed only 1 to 1.5 billion years ago. Imagine the planet slowly cooling enough for iron to crystallize at its very heart, a late-blooming jewel. This relatively recent formation could potentially explain the noticeable strengthening of Earth's magnetic field in its more recent geological past. Another intriguing mystery lies in the inner core subtle asymmetry. Seismic waves, those tireless travelers, move at slightly different speeds depending on the direction they pass through it, subtly hinting that one side of the core may be cooling or growing faster than the other. Some researchers propose that heat might be escaping unevenly, or that compositional differences exist between the eastern and western hemispheres of the core. Yet so far, no single model fully explains all the observed data. Why does the universe always do this to you, leaving just enough mystery? There's even compelling evidence suggesting that layers exist within the inner core itself, solid inner core, perhaps, with different crystal orientations or structural properties. This would imply that the deepest part of Earth has its own unique history and internal complexity, a kind of planet within a planet, with its dynamics still unfolding in profound silence. As we gently adjust our course, preparing to leave the heart of Earth behind and journey outward once again, we do so with a sense of quiet humility. For all our advanced tools and intricate models, the true heart of our home world remains largely unknown, realm of unimaginable fire and metal, spinning in profound silence far beneath our feet. Our journey, you see, is just beginning again. To truly understand the colossal engine that drives Earth's internal processes, the slow, majestic drifting of continents, the fiery rise of volcanoes, the subtle, constant motion of the crust, we must now turn our attention to a single fundamental force: heat. Heat is what keeps the culture. You might notice a faint hum, a deep, rhythmic vibration resonating through the hull, almost too subtle to pinpoint a whisper of our engines guiding us through the silent void. From this gentle perch, you can gaze upon a world brimming with its own internal energy, an intricate dance of heat beneath its rocky skin that powers its very existence. It sculpts mountains, cradles oceans, and generates the protective shield that wraps around it. Yet the source of such enduring vitality isn't immediately obvious, is it? Two ancient fires burn deep within that distant globe, fires ignited billions of years ago and still smoldering. The first, a truly ancient warmth, is a leftover from the planet's violent infancy. Imagine, if you will, over 4.5 billion years ago, a nascent Earth, a swirling tempest of colliding asteroids and planetary debris. Each impact, a cosmic hammer blow, compressed and heated the growing mass until it glowed, a molten sphere in the early solar system. As it slowly began to cool and solidify, much of that incredible, searing heat remained trapped deep within its core, a primordial ember. Even now, eons later, that original warmth gradually seeps upwards, a slow, gentle leak of energy flowing from the deep interior. You can almost feel the residual heat, can't you? But that ancient, diminishing fire alone wouldn't have been enough to keep a planet dynamically alive for so long. No, there's a second, more constant furnace at work, a quiet, persistent glow deep inside. Radioactive decay. Hidden within the crust and upper mantle are certain elements, unstable isotopes, patiently transforming into more stable forms. As they do, they release a steady, continuous stream of heat, a subtle, internal warming that never truly ceases. It's this sustained warmth that fuels the majestic internal currents of the mantle, ignites volcanoes, and, quite remarkably, sustains the very magnetic field that deflects the sun's harsh winds. Think of it, the dying echoes of a colossal birth mingling with the steady pulse of atomic decay, together breathing life into a world. The deep quiet of our own vessel, with only the soft murmur of recycled air around you, makes it easier to contemplate these colossal unseen processes. Heat, you see, is never truly still. From the deepest core to the outermost crust, energy is always seeking balance, always moving from warmer places to cooler ones. It's this ceaseless journey, more than just the sources themselves, that actively reshapes a planet. Scientists have observed 3 primary ways this heat makes its grand journey. The most straightforward is conduction, gentle, direct transfer. Much like the slow warmth that creeps up a metal spoon left in a hot mug of synth tea. Inside Earth, conduction allows heat to patiently meander from one solid, relatively unmoving layer to the next. Imagine the hot mantle slowly warming the cooler rock at the base of the crust, molecule by molecule. Rocks aren't particularly eager conductors, so it's a wonderfully unhurried process, a steady, gradual ascent of warmth through static layers. But then there's convection, the truly dramatic choreographer of internal heat. This is heat on the move, through the actual motion of material itself, fluid rock, in Earth's case, moving with the patience of geological time. As mantle rock absorbs heat from below, it subtly lightens, becoming less dense, and slowly, majestically, begins to rise. Meanwhile, cooler, denser rock, having released some of its heat closer to the surface, begins its slow descent, sinking back down to be reheated. This creates enormous circular currents, grand, looping rivers of rock, tirelessly carrying warmth upwards and bringing cooler material down. Isn't that just like space? Always with its vast, patient cycles. Radiation, the third method, is how the sun's warmth reaches us out here through electromagnetic waves. But deep inside a planet, shielded by countless miles of rock, its role is quite minor, a whisper at the atomic scale compared to the thunder of convection and the quiet persistence of conduction. These two, especially convection in the deep mantle, are the tireless sculptors of geologic change. Indeed, it is convection, more than any other mechanism, that orchestrates the grand planetary ballet of Earth's surface. Those enormous looping currents of mantle rock, warmed by the primordial heat and the steady radioactive glow, circulate at an astonishingly slow pace, just a few inches each year. Yet this glacial movement is incredibly powerful. The tectonic plates, those vast rocky rafts that form the planet's outer shell, simply float atop this slowly churning mantle, carried along like leaves on a sluggish river. Where this internal material rises, it gently pushes plates apart, creating what we call divergent boundaries. Think of the mid-ocean ridges, vast undersea mountain ranges, where fresh magma quietly wells up, solidifying to form new crust, ever so slowly spreading the ocean floor outwards. Conversely, where mantle material cools and sinks, often pulling a cooler, denser plate down with it, we find convergent boundaries. Here, one plate bravely dives beneath another, a process known as subduction, disappearing back into the fiery depths of the mantle. This sinking plate carries with it ancient water, sediments, and crustal material, which then melt, fueling the explosive volcanic activity we witness above. These are the powerful subduction zones, the sites of breathtakingly deep ocean trenches, towering volcanoes, and the shuddering tremors of powerful earthquakes. All of it, even the seemingly stable continental interiors, aren't immune to this slow, persistent motion. The subtle rising and sinking of that deep mantle material can cause entire regions to gently swell or slowly sag over unimaginable spans of time. It might lift a vast plateau into the sky, or quietly pull apart the land to open new rift valleys, even subtly altering ancient river systems. The connection is truly profound, isn't it? Heat, in its relentless journey, transforms into motion, and that motion, in turn, becomes the very sculptor of a planet's surface. Every mountain peak, every deep basin, every subtle fault line is a silent, enduring testament to the steady, upward flow of thermal energy from within. And while you might perceive the surface as utterly still, the deep earth, you understand, is always, always moving. Deep within that world, that silent warmth does more than merely move. It builds immense pressure, melts solid rock, and fuels some of the most dramatic spectacles imaginable on the surface. One of the most visible, most fiery expressions of this internal heat is volcanic activity, where molten rock, magma formed deep in the mantle or lower crust, finds its tumultuous way to the surface. It erupts in a dramatic ballet of lava, ash, and gas, a true planetary exhalation. Volcanoes exist because the Earth's interior is hot enough to partially liquefy solid rock. In those subduction zones we just spoke of, the water and minerals dragged down by the sinking plate actually lower the melting point of the surrounding rock, allowing magma to form. Meanwhile, in rift zones, where plates are gently pulled apart, the rapid drop in pressure also causes rock to melt. And then there are the enigmatic mantle plumes, rising columns of intensely hot material that pierce through the crust, creating hotspots, fixed points where magma continually rises, patiently collecting in vast chambers. From our tranquil vantage point, suspended in the gentle hum of the ship, you might peer out at a distant, glowing world, or perhaps just let your thoughts drift to the incredible forces shaping even the most serene celestial bodies. Deep beneath a planet's skin, unseen energies gather, with gases trapped in molten rock beginning to expand, pushing relentlessly against the layers above. This immense pressure will eventually breach the surface, sometimes in a slow, mesmerizing flow of liquid stone, other times in a breathtaking explosion of fire and ash. Each magnificent eruption, you realize, is the grand finale of a journey born from the deep. Hidden warmth radiating from the planet's very heart. Nothing to worry about, probably. Yet, that same profound heat can also express itself in far more peaceful ways. A quiet, continuous release of Earth's internal warmth, often seen in geothermal wonders. Imagine picturesque landscapes like those of Iceland, the volcanic fields of New Zealand, or the steaming basins of Yellowstone National Park, where groundwater slowly filters deep below. It's there in the quiet darkness that it encounters hot rock or magma, heating until it surges back upwards, emerging as serene geysers, inviting hot springs, whispering steam vents, or even gently bubbling mud pools. These features, though seemingly placid compared to a volcano's fiery roar, are simply different expressions of the same deep-seated planetary heat, a continuous, low-level pulse. We, as humans, have found ingenious ways to tap into this elemental warmth, a testament to our enduring curiosity. In some parts of our home world, you'll find wells drilled deep into the earth, drawing up superheated water or steam to warm buildings or generate electricity. It's a clean, remarkably sustainable energy source, practically limitless as long as the planet continues its gradual internal cooling from within. But isn't that just like space? Everything is in motion, everything is changing, even if it takes geologic eons. Earth has been steadily shedding its heat into the vast, indifferent void, radiating thermal energy outwards, conducting warmth from its fiery interior through the crust, and finally into the oceans and atmosphere above. This flow of heat is almost imperceptibly slow, a mere whisper of energy per square meter. Yet, when spread across the entire surface of a world, it culminates in a significant loss over time. The planet's energy balance is a complex dance, a cosmic waltz between receiving energy from the decay of radioactive elements and retaining some of its primordial warmth, even as it cools. You might need a moment to just float here, considering the scale of it all. 4 billion years ago, Earth was an entirely different beast, far more geologically active, with colossal volcanic eruptions, a thinner crust, and a scorching mantle. Plate tectonics, that slow, grinding engine of continents, likely operated in wildly different ways then, and the core's molten heart may have behaved with much greater chaos. As Earth continues its cooling, these subtle transformations persist. The planet's solid inner core, for example, is steadily growing, slowly crystallizing more iron from the liquid outer core. This process, in turn, releases additional heat and lighter elements into the outer core, effectively sustaining the planet's powerful geodynamo, that engine generating its magnetic shield, for a little while longer. But over billions of years, as those radioactive elements eventually decay and the core gradually loses more energy, this living planet will undoubtedly become geologically quieter. Its magnificent magnetic field might weaken, the mantle's vast currents could slow, and its tectonic plates might, one day, simply grind to a halt. Of course, that particular future is so unimaginably distant that it feels like another universe entirely. For now, Earth remains vibrantly alive, its internal heat steadily flowing outwards, powering all its motion, all its change, and ultimately, life itself. Though hidden deep within the planetary interior, this magnificent warmth has effects that reach far beyond mere rock and crust. One of its most profound influences is on the very magnetic field that envelops our world, a field not static and fixed, but dynamic and ever-changing. These magnetic fluctuations, everything from subtle drifts to dramatic full reversals, are ultimately orchestrated by the heat churning through the core, the majestic ballet of molten iron within the outer core, driven by convection and profoundly influenced by Earth's own graceful spin, is precisely what generates this vital magnetic field. Yet, this intricate movement is finely tuned by how heat manages to escape from the core into the overlying mantle. When heat flows efficiently, perhaps into areas where the lower mantle is cooler and more stable, the convection in the outer core becomes more robust and organized. This, in turn, strengthens the magnetic field, enhancing its stability, like a steady planetary breath. But isn't it curious how tiny differences can have such grand effects? Conversely, in regions where the mantle might be hotter or more sluggish, the flow of heat from the core can slow down, much like a thick syrup. When this happens, the convection within the outer core loses some of its vigor, and the magnetic field can weaken or become noticeably more chaotic. These regional variations help us understand why the magnetic field isn't perfectly uniform across the entire planet, why it possesses patches of intense strength in some places and weaker zones in others. It's a living, breathing shield, constantly adjusting. Over truly vast timescales, the field undergoes these grand geomagnetic reversals, where the north and south magnetic poles dramatically swap places. These spectacular reversals occur irregularly, roughly every few 100,000 years, and appear to be intimately linked to profound shifts in the flow patterns of the outer core, though the exact mechanisms still whisper their secrets. Many scientists believe that subtle changes in the thermal balance between the core and the mantle play a key role, gently altering the patterns of fluid motion that sustain the powerful geodynamo. Even without full reversals, you'll observe the magnetic field is perpetually drifting. The magnetic North Pole, for instance, is currently journeying across the Arctic at dozens of kilometers per year. A quiet observation from our console screens reflecting deep earth changes that slowly ripple outward. In this magnificent way, Earth's intricate heat flow doesn't merely sculpt rock and landscape. It also shapes invisible forces. It creates planetary-scale systems that protect life from harsh cosmic radiation, guide migratory animals across continents, and interact profoundly with the space environment around us. But perhaps the most familiar and dramatic expression of Earth's internal heat is visible in its surface geology, in that undeniable relationship between deep warmth and the landscapes we see. Volcanoes, towering mountain ranges, seismic earthquakes, vast rift valleys, and abyssal ocean trenches are all dramatic surface manifestations of these deeper thermal processes, a constant reminder of the energy beneath. When the mantle convects, it gracefully shunts the tectonic plates across the planet's face. And when these colossal plates either collide or gracefully diverge, the crust responds with profound deformation, majestic uplift, or spectacular volcanic eruptions. When molten magma rises toward the surface, it carries with it immense heat, intense pressure, and new material into the crust, altering ecosystems, building entirely new land, and at times, dramatically reshaping entire regions. Even more subtle changes, like the slow warping of continents, the gradual rise and fall of coastlines, or the sagging of land beneath ancient glaciers, are often intricately tied to variations in heat flow and the majestic slow movement of the mantle. Over millions of years, vast regions of a planet rise or sink in direct response to the mantle's shifting. Unseen currents, which are themselves driven by temperature differences deep below. In a profound sense, the Earth's surface, from our quiet observation deck, is like a living skin, one that flexes, breathes, and moves in graceful response to these powerful internal forces. It may feel steadfast and still beneath our feet, but it is anything but static. The incredible warmth beneath us is perpetually at work, lifting one continent, gently lowering another, in an eternal, silent dance. Watching as one massive segment gives way, then another, a slow-motion dance that cracks open the brittle outer shell and fuses it anew. You can feel a phantom warmth even here, a subtle shift in the recycled air around you, a hint of the immense energies deep within these worlds. While we float far above, untouched by the raw, molten heart of a planet, its presence shapes everything we observe. It's etched into the grand, sweeping arcs of its mountain ranges, dictates the meandering courses of its rivers, whispers in the occasional, almost imperceptible tremor of its surface, and breathes out in the gentle mists from subterranean springs. This incredible inner warmth continually writes the very story of the world, both in its hidden depths and on its luminous face. Most of a planet's grand internal alchemy unfolds in profound silence, miles beneath its shimmering crust. Yet, its most spectacular moments, the grand pronouncements of its deep-seated power, often manifests with startling suddenness on the surface. You might catch a fleeting glint of reflected starlight on a console display, perhaps indicating a new energy signature. Two of the most vivid, most dramatic expressions of these hidden processes are what we call planetary shudders or quakes, and fiery effusions from its core. These aren't quiet, slow movements. They begin as imperceptible stresses far below, then erupt into violent events above in mere moments. Isn't that just like a world? These are truly the loudest whispers of a planet's inner voice, a profound utterance from the abyss. What drives these planetary shudders? It's a colossal buildup of internal pressure within the world's outermost shell, which then releases itself in an instant. Imagine the distant, rhythmic thrum of our ship's engines, a constant, low vibration mirroring the planet's own internal motions. Its entire surface is actually a mosaic of immense, rigid crustal plates, endlessly, imperceptibly gliding across the more pliable mantle beneath. These aren't smooth transitions, as these colossal segments grind past one another, or perhaps tragically collide, or even gently pull apart. Friction often locks them into a silent, cosmic embrace, resisting movement, nothing to worry about, probably, but pressure, like any contained force, builds to an unsustainable peak. Then, in a sudden, dramatic lurch, the rigid rock gives way, fracturing or shifting along a deep, invisible fault line. You might need a moment to just float here, letting the quiet of the void envelop you, imagining that immense, sudden release. This explosive energy radiates outward in every conceivable direction, manifesting as powerful seismic waves. The exact point deep within the world where this rupture originates is known as the asterisk focus asterisk, and the spot directly above it, on the planet's glittering surface, is the asterisk epicenter asterisk. The deep movement then causes the surface to tremble, sometimes subtly, sometimes with catastrophic force, depending on the raw magnitude of the event and the surrounding material's composition. When these incredible planetary shudders occur, they don't just create one kind of vibration. They send out two distinct types of seismic waves, each carrying its own secrets through the planet's layers. First, there are the primary waves, or P waves. These are like gentle whispers through the void, though far more powerful compression waves that surge forward, rapidly squeezing and expanding the material they travel through, much as sound does through our ship's recycled atmosphere. They're remarkably fast, slicing through solid rock, molten liquid, and even gas. These swift messengers are always the first to arrive at any planetary monitoring station, delivering their urgent news of deep upheaval. Then come the secondary waves, or S waves, traveling a little more leisurely. These move the planet's material in a different dance, swaying it from side to side or up and down, much like you might ripple a rope held taut in zero gravity. What's truly fascinating about S waves, though, is their strict preference. They can only travel through solids. They simply cannot pass through liquids. This crucial distinction has offered us incredible insights into a world's hidden structure. Imagine the silent console lights of our instruments, tracking these subtle differences, revealing the very heart of a planet. If S waves encounter a layer they can't cross, we know that deep region must be liquid, like the swirling, molten outer core. By carefully analyzing the precise arrival times and unique behavior of both P and S waves at various observation points scattered across a planet's surface, we can construct an astonishingly detailed map of its internal architecture. It's like using echoes in a vast, dark cavern to understand its hidden contours. The way these seismic waves bend, reflect, or mysteriously vanish tells us exactly where one layer transitions to another, from the rigid crust to the viscous mantle, and deep down to the fiery core itself. It even helps us decipher the varying temperatures and densities within those inaccessible depths. Isn't that just like space, always offering new ways to see the unseen? Yet, beyond their profound scientific utility in revealing a world's secrets, these planetary tremors resonate on a deeper, more primal level for any beings who experience them firsthand. The sudden, violent trembling of their ground, the unsettling groan of structures, that chilling quiet just before an aftershock. These aren't just data points. They are stark, visceral reminders that the very world beneath them is a living, breathing entity, its tranquil surface inextricably linked to a colossal, ancient story unfolding miles below. Now, as we shift our gaze slightly, allowing the gentle pull of the ship's artificial gravity to settle you, we'll dive into how these deep movements sculpt the landscape through both quakes and the spectacular fiery outpourings we call volcanic eruptions. It's all part of understanding the restless heart of a living world. If planetary shudders represent a world's sudden, explosive release of pent-up stress, then volcanoes, or rather, their fiery vents, are its gradual, often spectacular exhalations of profound internal heat. You can almost feel the temperature shifting subtly here in the cabin, a gentle warmth from the nearby heating vents, mimicking the planet's own thermal story. They emerge where molten rock, which we call magma, finds a pathway, slowly ascending through the world's crust, eventually bursting forth onto the surface as glowing lava, dense ash, and scorching gases. Every single one of these magnificent fiery structures is deeply connected to a process born miles underground, where intense heat melts solid rock and sets it into powerful, flowing motion. These fiery spectacles manifest in various pivotal geological environments across a world's surface, each type sculpted by a unique interaction between those same colossal crustal plates. Look closely at the faint energy readings on your console, a silent story unfolding along what we term divergent boundaries, where two plates are slowly, steadily pulling away from each other. The mantle's molten heart senses the opening. Magma rises to fill this ever-widening gap. We see this occurring at vast suboceanic rifts, where new planetary crust is ceaselessly being forged by a steady procession of deep underwater eruptions. These hidden vents, rarely glimpsed, are nonetheless among the most prolific on any ocean-covered world. Then, at convergent boundaries, the dance is far more dramatic. One immense plate dives headfirst beneath another, slowly descending into the planet's mantle. As this sinking plate carries trapped water and minerals deep within, it acts as a catalyst, subtly lowering the melting point of the surrounding intensely hot rock. This allows it to partially liquefy and begin its slow, inexorable ascent towards the surface. The outcome is often a breathtaking chain of towering, steep-sided volcanoes, prone to explosive, dramatic eruptions, much like those magnificent fiery peaks that encircle the Pacific in what's often called the Ring of Fire. Why does the universe always do this to you? It puts on such a show. And sometimes, far from these plate boundaries, volcanoes emerge from what we call mantle plumes, colossal columns of superheated material ascending directly from the deep mantle, puncturing through the overlying crust. These hotspots are like fixed, fiery beacons in the planet's interior. As a crustal plate slowly, majestically drifts over one of these stationary plumes, it gives birth to a succession of volcanic islands, each one forming, living, and then moving on, creating breathtaking chains across the vast oceans. Think of worlds like Hawaii or the Galapagos, where a trail of fiery peaks tells the silent story of a continent's slow, deliberate journey. The character of a volcanic eruption, however, is not a fixed thing. It changes dramatically based on the magma's specific composition and its internal temperature. Consider, for instance, basaltic magma. It's incredibly hot with a low silica content, which means it flows with an almost liquid grace, leading to relatively gentle, effusive eruptions. These build what we term shield volcanoes, vast, gently sloping landforms, often so wide they encompass entire regions. Much like Mauna Loa, the lava simply cascades outwards in thin, incandescent sheets, gliding for immense distances across the landscape before it gradually cools and solidifies. In stark contrast, magmas rich in silica, like andesitic or rhyolitic types, are cooler and significantly thicker, almost molasses-like in their viscosity. This dense consistency means they tend to trap gases far more effectively, leading to an insidious buildup of immense pressure deep within the magma chamber. You can feel the subtle, almost imperceptible shift in the ship's gentle forward momentum, a reminder of contained power. This internal pressure grows, silent and relentless, until it reaches a critical point, a cosmic breaking threshold. Why does the universe always hide such explosive power beneath such quiet surfaces? When that internal pressure eventually exceeds its containment, it triggers a truly violent eruption, blasting colossal plumes of ash, rock, and superheated gas high into the planet's atmosphere. The soft glow of the console lights can barely capture the imagination of such a spectacle. These spectacular, often destructive, events forge steep-sided stratovolcanoes, towering peaks reminiscent of Mount St. Helens or the iconic Mount Fuji. Their eruptions are sudden, dramatic, and can reshape an entire landscape in a single cataclysmic instant. A magma's journey may begin deep in the planet's heart, but its winding, complex path to the surface is a saga of immense geological power. We're simply drifting now, bathed in the soft, ambient glow of the navigation console, a gentle hum resonating faintly through the ship's hull. The recycled air feels cool against your skin as the gentle, almost imperceptible shift in gravity reminds you of our quiet momentum. You glance out past the star-dusted viewport, and the cosmic canvas unfolds, a silent invitation to wonder. Imagine, for a moment, peering through the immense, rocky shell of a world far below us, or perhaps an alien sphere yet to be discovered. Somewhere deep within its fiery heart, a profound transformation is silently underway. Beneath the planet's surface, nestled within its mantle, incredible pressures and temperatures are at play. Conditions shift us, subtle change in heat, perhaps a slight variation in pressure, or even just a unique blend of minerals and rock begins to yield. A fraction of it liquefies, turning into molten stone, shimmering with untold energy. This nascent magma, now lighter than the solid rock around it, begins an inexorable, upward journey. It's a slow, persistent ascent, isn't it? Pushing through unseen fractures and tiny weaknesses, seeking a path toward the light, or at least the surface. Sometimes, this molten river finds a temporary respite, pooling in vast, underground chambers. Think of them as immense subterranean lakes, quietly collecting liquid fire over centuries. They can lie dormant for ages, building in volume and pressure, a patient, simmering force. Then, when the reservoir finally brims, or a new fissure cracks open a fresh escape route, the chamber might just exhale. A grand eruption, a planetary breath. The manner of its release, a gentle flowing sigh or an explosive roar, depends on how quickly that internal pressure builds and how easily its trapped gases can escape. Isn't that just like the universe, always finding its own dramatic timing? Even after such a dramatic release, the molten heart often remains restless, continuing to pulse with activity, keeping the system alive. Some worlds might experience a continuous, slow outpouring of lava, a steady sigh of gas, a constant geological whisper. Others will remain silent for millennia, holding their immense potential energy captive until a new cycle awakens them. From the very first moment that rock melts deep inside to that breathtaking instant it breaches the surface, these fiery manifestations are vivid, potent reminders of the sheer, unimaginable heat churning within a planet's core. Now, from our vantage point here in the tranquil void, you might see earthquakes and volcanoes as separate phenomena, one driven by immense pressure, the other by profound heat. But look closer, feel the soft vibrations of our ship's engine, and you'll sense a deeper connection. They are intimately linked, these planetary expressions, both arising from the dynamic movement of a world's tectonic plates. Most commonly, they converge along these colossal plate boundaries, where the crust is in constant, grinding motion. These are the planet's seams, its active lines of growth and destruction. At what we call divergent boundaries, plates gently pull apart as they slowly recede from each other. Like silent dancers, fresh magma rises to fill the gaping chasm. It forms new crust in a continuous, incredibly slow process, building new land as we watch, or rather, as the centuries unfold. These spreading centers are often rather quiet, even serene, producing a constant background hum of gentle tremors and underwater volcanic activity. They tirelessly create vast, sprawling oceanic ridges across the seafloor, an unending, quiet construction project that shapes worlds. Then we have convergent boundaries, where one plate solemnly descends beneath another, into what we call a subduction zone. This is where the real drama unfolds, creating both immense, powerful earthquakes and fiercely explosive volcanoes. As that subducting plate is forced deep downward, an unimaginable stress slowly accumulates along the interface where the two titanic plates grind together. Eventually, that stress simply has to release, and when it does, it's often a massive earthquake, a sudden, violent shudder that, if it happens beneath an ocean, can birth devastating tsunamis.